I'd like to just say, please forgive me if the handwriting is messier than normal. My son ripped the tip off of my stylus. Alright, with pyruvate carboxylase, it's of special interest because of its structural, catalytic, and allosteric properties. We have an N-terminal domain, which is from amino acid 300 to 350, okay, which is an ATP grasp. Domain. We have a C-terminal domain, which is 80 amino acids. And this is our biotin binding domain. Okay. The biotin transfers activated carbon dioxide, and it has a swinging arm. And we'll see this mechanism again when we look at fatty acid biosynthesis. The carboxylation of pyruvate takes place in 3 stages. In the first stage, we have carbonic acid plus ATP. We're going to hydrolyze that ATP and make an activated carbon dioxide. In the second stage, we have biotin linked to the enzyme. This can now bind the activated carbon dioxide. We get our CO2 biotin attached to the enzyme, plus inorganic phosphate. In the final stage, we have the carboxylation of pyruvate. To give us the biotinylated enzyme again and our new oxaloacetate. Alright, just to show you the chemistry of this reaction here. Okay, we have our carbonic acid. It shows the oxygen attacking the phosphate. We release ADP, and here is our activated carbon dioxide. Now we have biotin. Okay. The nitrogen can attack the carbon. We lose this phosphate. This reaction is favorable because we have more resonance. When we release inorganic phosphate, and we have less charge repulsion. Now we have our activated biotin, so to speak, with our carbon dioxide. We have pyruvate, where we've removed a hydrogen, and this is by a basic amino acid in the enzyme site. Okay. The carbon can then attack the carbonyl, and as a result, okay, we carboxylate and we make oxaloacetate. So again, remember this reaction is driven by ATP. I would like to note that biotin is not carboxylated unless acetyl-CoA is bound to an allosteric site. Okay, this is an important physiological control mechanism. And we'll look at this in more detail when we look at the tricarboxylic acid cycle. Alright, as I said before, pyruvate carboxylase is a mitochondrial enzyme. Okay. And other enzymes of gluconeogenesis are in the cytoplasm. So we have to get the oxaloacetate out of the mitochondria. Now, oxaloacetate cannot cross the mitochondrial membrane. So we use what's called the malate shuttle to get oxaloacetate across. Alright, we've converted pyruvate to oxaloacetate. In the mitochondria we have a malate dehydrogenase. This malate dehydrogenase is going to reduce oxaloacetate to malate. Okay? And we generate NAD+. Now the malate can cross the mitochondrial membrane. The malate in the cytoplasm is converted back to oxaloacetate by malate dehydrogenase, and it's reoxidized into oxaloacetate. Now this malate shuttle can also be found in the tricarboxylic acid cycle, or the Krebs cycle. However, the overall flow of metabolites in the two processes is in opposite directions. So for TCA, you're using malate to get oxaloacetate into the mitochondria. In gluconeogenesis, we are using malate to get oxaloacetate out. Okay, so that's the difference. Okay, next we're going to take oxaloacetate. We are going to decarboxylate and then phosphorylate. This reaction is catalyzed by phosphoenolpyruvate carboxykinase, and the product is PEP. This is a reaction where we have decarboxylation to drive an unfavorable reaction and here our phosphoryl donor is GTP. So if we look at the reaction here, we have our oxaloacetate and GTP, our phosphoenolpyruvate carboxykinase, or PEPCK, and our product is phosphoenolpyruvate, GDP, and carbon dioxide. If you note, when we made PEP, we got out 1 ATP in glycolysis. To go in the opposite direction, it costs 1 ATP and 1 GTP. The delta G for this reaction is negative 25 kilojoules per mole. So these two steps are essentially irreversible. One more note about this reaction. There's a logic to that malate shuttle that we saw. Okay. The NADH to NAD plus ratio in the cytoplasm is 8 times 10 to the minus 4. This is about 10 to the 5th lower than in the mitochondria. Because we consume NADH in gluconeogenesis, we are able to regenerate NADH when we go from malate to oxaloacetate. And so we need these reducing equivalents to allow gluconeogenesis to proceed in the cytoplasm.